was also going to ask, because I found a library for R that does specifically the nice pie charts. Would it be okay to use that library?
With the Carolina library.
Yeah.
Yeah, I read that one too.
I did.
I didn't get it, but I read it.
I had no read that.
It's gonna be right. That's the one that we will use. But technically, you could do it in different ways, but yeah.
Mhm.
So there is that example that I didn't go through the pie chart.
Mhm.
You guys were supposed to look at that code, but that code would basically step by step regenerate that pie chart one slice at a time. So that's another way to do it. Yes.
On the same problem, what are you expecting for the report? Do you want a triple AI formatted report, or could it just be like a Google Doc? And we just
Triple AI.
Triple AI?
When is the deadline?
I'm sorry?
When was the deadline for okay?
Friday
At 1 a.m.
at 1 a.m.
Okay, so is everybody on time or do you feel like? Right? Alright. That's awesome.
Do we have to do Friday at midnight instead of Friday at 1 a.m.? It's due basically Thursday at night and not Friday. We don't get Friday to work on it. We have to do it, it's basically due tomorrow. That's late.
Yeah, we can do it on Friday. Midnight. I can extend it. Okay, oh, I forgot to ask, from people who are online. Can you all hear me? Yes, no? Okay. All right. So for today, we've got two options. One of them is to start talking about time series and graphical integrity, or we finish the LMM lecture. We still have a couple of sections of the hands-on session that we haven't finished. Which one do you prefer? Do you want to continue with theory as we decided to do before, or we could just wrap up R and LMM, and then after that, it's just going to be theory.
Which option will push off the next homework more?
It's a good thing that you brought up because I've been thinking about it. I'm concerned with the amount of time you guys are going to have for your project. Okay, so technically the project is going to be left with 1 or 2 weeks at the end of the semester. Those 1 or 2 weeks are the 1 or 2 weeks you're wrapping up with other projects at the same time doing the exams. So, one way that I was thinking of was that I could basically have an extended version of Homework 3 as a project. Which means that there is a good thing about it and there's a bad thing about it. The bad thing about it is that your grades for 4 homeworks are now going to be decided on the basis of 3 homeworks. So if you screw up something, you're going to pay more for it. So that's a bad thing. The good thing about it is obviously it's going to be a bit of less workload. And so far, I'm not sure how you feel about it, but the homeworks in this class, there are only 3 of them, but they weren't that easy. It requires a lot of work to make it happen the way that the actual thing looks like, right? It's not as that simple. It's designed to be like that because I wanted you guys to have a lot of hands-on work. So you actually figure out how art can be played to create some incredible graphics. So you tell me which option you want.
Yeah.
I've got the homework to you. I can release it today, right now. I can release it. And I've got the final project. I can release that as well. But I feel like you're not going to be able to finish the final project in 2 weeks. It's going to be a lot of work. So who is in favor of the extended version? Who is in favor of having this?
What would the extended version look like?
It looks like a proper final project that you're gonna have like 3 to 4 weeks to do. I can release that probably on Monday. Then you're gonna have 3 weeks to do.
And just to clarify, if you did the extended version, you released it on Monday, that would be kind of like it for the rest of the semester, but we have the rest of the semester to work on.
Yeah, but you've got the rest of the semester as well. And you've got the rest of the semester to completely with the problems with that. But in the last 2 weeks, you probably have like 1 week to come to me. And remember, you also have homework 1 that I'm sure nobody did. Good for you. Have I shared the folder for that? I didn't.
I don't think anyone's asked for it.
I thought I already did. I thought I put everybody in.
I haven't gotten it yet.
I'm gonna check it again to make sure. If it's not there, then I have to, maybe I invite a bunch of people from the other class. Which is interesting, they didn't say. If you've got it, then you have to upload it. And remember, that wasn't just during the lecture, it was also providing feedback on 3 other lectures. So you're not done yet. You have at least 3 to 4 hours. Okay. So it's up to you guys. What do you want to do? Make a decision. Let's move on.
I'm personally in favor of the first one. I'd rather have a bigger project with more time to come to you with problems.
Okay. What about you guys?
I agree.
So I can tell you what the project is going to be about. Sorry, what the extended version is going to be about. Linear mixed model is very important. It's a type of analysis that would separate you from everybody else who apply for a job when you know it, and you can use it. So it's going to be about linear mixed models. So it's going to be a version of homework 3, but it's also going to have another question added to it, which is going to be something equivalent to that pie chart that you're doing, but with different job. So you have to recreate another one of those, which is quite complex, difficult to do. So that's a first. And then you have to write the report on both. Okay? So is that what you want to do? Somebody say something.
Yeah.
I'm recording your voice as well.
Oh.
I cannot record your faces. All right. So are you guys okay with this in the online session? Either yes or no. Okay. All right. So that's what we are going to do. We are going to mix our project, final project and homework 3. In order to release that, then I need to finish the mixed model today, which means that let me. What's this? What was this? All right. All right. Okay, so that's this. I just need to join that meeting. So let me- Can you guys hear me? Okay, let me turn this thing on. And come here, share the screen. There we go. Can you please confirm that you see the screen and there is no problem so we can start? All right. So let's continue and finalize linear mixed model effects. And then we get to the rest of the theory, which are going to be very interesting concepts that we will be talking about on starting on next week. So before we get any further, this is just to again remind us to be careful with our health and try to cover your cough and wash your hands and stay home when you're sick, and try to prevent touching your eyes and nose and mouth. And this one is, if you're interested to join this student outreach of ACM, send me an email. With this one, we are running this study and we are looking for volunteers who want to join us in this study, who have at least 6 months of experience with C or C++ programming. And you would be compensated for your time and effort, receiving $45 for the 2 sessions that you get involved in. We would be recording EEG and eye tracking data, and we want to see how the brain reacts to various code snippets. If you're interested, please send me an email or send an email to Dr. Zhang, and somebody from the team would contact you later on and set up a time that works for you to do the recording. Okay, the disclaimer is we will be using material from Gabriela Ajduk. And can you please confirm that you can hear this? Does the sound come true? Okay, you can hear the video, so I have to share it again. And this time, yeah, that's the problem. All right, you should be hearing now. We are going to use data from a workshop where they use this very interesting data set called Dragons. It's a fictional study system. You are going to have this data through just give me a second, sorry. for the file that I would be uploading to the canvas. But let's take a look at it. Let's load this file. Take a look at the head. We've got site, we've got X, then we've got mountain range, body length, and test score. So this is the data set for the dragons. Imagine that we want to decide to train dragons, and so we basically went and gather these data on Dragonite intelligence. So that's gonna be the test score field that we've got in here. Then we also get information about the dragon's body range, body length. We got this information from different sites, and from different mountains, or like a mountain range, or this is equivalent to something like a region or something. So we load the data, we looked at the head of it. Now let's say we want to know how the body length of the dragons basically impact their test score. Before moving any forward, we are going to look at the distribution of the response variable, which is the dragon test score in here. So here it is. We create a histogram of it. It's a good practice to standardize your exploratory variables before proceeding, so that they have a mean of 0 and a standard deviation of 1. So mean of 0 is referred to as centering, and whenever you've got standard deviation of 1, it's called a scaling. If you do something like that, it basically ensures that the estimated coefficients are all on the same scale, making it easier to compare effect sizes. In order to do something like that, we can use a function called scale. So here we go. First of all, let's look at this value, dragon body length. This is what you get, and then now we are gonna scale it. If we look at this one, it's now scaled and centered, and everything is ready to go. We could basically do this in a slightly different way. We could, for example, say something like this. Use a slightly different version. So in this version, we are saying center should be true, scale should be true. Everything else is the same. Now let's look at this. Inside here, we've got body length 2 and 3. 3 is the one that we just created. Let's get to the end. As you can see, every single entry is the same. So it means that these values that are set in here are basically the default value. So whenever you call the scale without setting anything else, then it assumes that the center is supposed to be true and the scale should be true. But if you need it for whatever reason to don't have to don't perform a centering, then you can just say center equal false. Or if you just wanted to do centering but not the scale, then you can make that false. Not that you commonly need to do something like that. But basically, SQL centers the data, which means that the column mean is going to be subtracted from the values in the column, and then scale it, which means that the centered column values are going to be divided by the column's standard deviation. So let's get back to what we were doing. We wanted to know, is the test score affected by body length? So let's say, for example, bigger body length, maybe lower test score or something like that. So we want to know if there is a relationship between these two. So first thing to do is to basically fit all the data in one analysis. One way to analyze this data would be to fit a linear model to all our data, ignoring the sites and the mountain ranges for now. So remember that our data had mountain range and site. So we can just ignore them. Let's run this one more time. And if you keep Ctrl-Shift and C, then you can basically comment something if you needed to. Now we've got the data the way we wanted. I didn't want to have that extra dragon body length tree. So, okay, we want to use a linear model for this. Now we are looking at the relationship between test score and body length 2. And we put that in basic.lm. We are using library LME4. Now let's look at the summary of this analysis. It seems like there's a significant difference. There's a significant relationship between these two. There's a significant difference between test scores based on taking into account the body length. But let's plot this. Let's look at the outcome. Here we go. We are going to use a ggplot, and in the ggplot, we said the data is going to be the dragons. The AES is setting X to be body length and Y to be test score. And this is going to be our ggplot, and we are putting GM points, geom points, and geom smooth on it. And the method for the smooth is going to be LM. Sorry. There we go. You should note that putting your entire ggplot code in brackets create a graph and then shows it in the plot viewer, as you saw in here. If you don't have the brackets, you've only create the object but haven't actually visualized it. So, what does this mean? This means that, for example, if I were to do something like this, instead of put a root there, so this allows the code to create the object and visualize it, but when I get rid of these brackets and I clean this thing up, just so we see what happens. As you can see, the object is created in here, but nothing gets visualized. So in order for you to be able to actually see the outcome, in addition to actually creating this, you need to put those brackets around it. So let's get it from top one more time. And there we go. Okay. Now,
So what we see is that from the linear model and from the plot itself, it seems like bigger dragons do better in our intelligent tests. That, which means that bigger the length is, the higher the test score. That seems a bit odd, so it shouldn't really impact the test score. So, but the question is, are the assumptions actually met? So let's plot the residuals. The red line should be nearly flat, like dash gray line. So here we go. This is the residual plot. And here is the QQ plot. What we are supposed to see is the points are supposed to be ideally fall onto the dragon dash line, which is this one. They are a little bit off at the extremes. Now the other question that we need to figure out is what about observation independence? Are they actually independent? Are the data independent or not? So we collected multiple samples from 8 mountain ranges for this data set. So it's perfectly plausible that the data within the mountain ranges are more similar to each other than the data from different mountain ranges. So meaning that there is some sort of correlation there, or there is some sort of dependence on the mountain ranges. So in order to have an understanding of what's happening there, we are going to do a box plot. Here we go. So we are doing a box plot of test scores with effects considered, fixed effects considered for mountain range. So we've got test score on the y-axis and mountain range on the x-axis. It seems like something is going on in there. But the other thing that we could actually look at was some sort of a scatter plot where we color code everything. So here's the code for this. We are using ggplot with dragons. In our AES, we are saying X is going to be the body length, Y is going to be the test score, and the color is going to be based on the mountain range. And we are putting a scatter plot or geom point with size 2 on this. And we are using a classic name. And we remove the legend position. There we go. From this plot, it looks like our mountain ranges vary both in the dragon body length and in their test score. This confirms that our observations from within each of the ranges aren't actually independent. We can't ignore that as we are starting to see, it could actually lead to completely erroneous conclusion. So the next step to do would be to run a multiple analysis. And in order to help everyone, let me add this in here. Running multiple analysis. Okay, now you wouldn't get confused in the code. So we could actually run many separate analyses and fit a regression for each of the mountain ranges. Here we go. What we are going to do is to have a quick look at the data split by mountain range. We are using a facet graph in here. So let me maximize this. Okay. So we are doing a ggplot with AES of body length and test score, data being dragons. We are putting a scatter plot plus a facet range with a fixed effect on mountain ranges, and the labels, the X labels being length and the Y label being test score. So this results in a breakdown on mountain range. As I said, it will cause a breakdown on mountain range, but in order to gain a better understanding, I call this function, which is calling the unique value on Dragon's mountain range. When we call this, as you can see, there are 8 levels, and they are Bavarian, Ligurian, Emmental, Central, Maritime, Southern, Julian, and Sarantal. And these are the same groups that you see in here. So this way we can have a look at each one of these mountain ranges separately, the data within each one of them separately. So we've got 8 analyses in here. We also have different sites in each mountain range, which, similarly to mountain ranges, aren't independent. So we could also run an analysis for each site in each range separately. So if we wanted to also consider the impact of the sites, then we have to estimate a slope and intercept parameter for each regression, right? First of all, we have to run an analysis for each site in each range separately. And we have to basically estimate a slope and intercept parameter for each regression, which means that we're going to have 2 parameters, 3 sites, and 8 mountain ranges. This is going to result in 48 parameter estimations, 2 by 3 by 8. In addition, the sample size for each analysis would be only something around 20 dragons per site. So this is going to be problematic for us because not only we are hugely decreasing our sample size, but we are also increasing chances of type 1 error, where you falsely reject the null hypothesis by carrying out multiple comparisons. This is not a good idea to do. So instead of that, what we are going to do is to modify the current model. Again, let me put the comment in here. So, what we want to use, what we want to do is to use all the data, but account for the data coming from different mountain ranges. For now, we're going to put site on hold, but we are going to get back to it. So here is the model that we've got. We are doing a linear model on test score with fixed effects of body length and mountain range. And we're calling that mountain LM. And if we get a summary of that, then it shows that there is significant difference on test score. And there are significant impacts on central mountain range, on Emmental mountain range, Julian, Ligurian, Maritime, Sarntal, and also southern. Remember that for these to be significant, the value that you see in here should be less than 0.05. As well as the time that they are, then there's a significant impact, which is what we see in all of these, with the exception of this one. The body length by itself does not have a significant, there isn't a significant difference within the values of body length. Okay. So let's think about what we are doing in here for a second. The model that we created is estimating the differences in test scores between the mountain ranges, and the problem is the issue is we are not actually interested in quantifying test scores for each specified mountain range. We just want to know whether body length impacts test scores, and we want to simply control for the variations coming from the mountain ranges. So that's what we basically refer to as a random effect. And this would basically arrive us at mixed effect models. So a mixed effect is a good choice here. It will allow us to use all the data we have, which means that we are going to have a higher sample size, and account for the correlation between data coming from the sites and mountain ranges. We will also estimate fewer parameters and avoid problems with multiple comparisons, as I explained before. So it's a very, very good approach to use it here. Again, we are using LME4. If you don't have it, you have to install it first. Let's load the library. Okay. So one thing to understand in here is the differences between the fixed and random effects. So an important thing to understand is that this difference has very little to do with the variables themselves, but it has a lot to do with the research question that you want to answer. So in many cases, the same variable could be considered either a random or a fixed effect, and sometimes even both of them at the same time. The thing is, you should always refer to your questions and hypotheses to construct your models accordingly. In the exercise that we are doing in here, we are looking to control for the effects of mountain range. We haven't actually sampled the mountain ranges in the world. We only have 8 of them in here in our data. So our data are just a sample of all these mountain ranges. We are not really interested in the effect of each specific mountain range in here. So we don't care what, well, it very much depends on what sort of analysis you're doing. But in this particular example, we don't care about the impact of each specific mountain range on test score. What we are hoping for is that our model would also be generalizable to dragons from other mountain ranges. But we know that the test scores from within the ranges might be correlated. So we want to control for that. If we specifically choose 8 particular mountain ranges beforehand, and we were interested in those ranges and wanted to make predictions about them, then mountain ranges would be fitted as a fixed effect. But in this example, it's going to be fitted as a random effect. So at the very end, it's going to come to these questions of what are you trying to do, what are you trying to make predictions about, and for the type of data that you've got and prediction that you've got, what would account for noise that you need to control for? If you can answer these, you can figure out which variable is going to be a fixed effect and which one is going to be called the random effect. Okay, now let's fit the model. So we have a response variable, which is called the test score in here, and we are planning to explain part of the variations in the test score through fitting the body length as a fixed effect. But the response variable has some residual variations or unexplained variation associated with the mountain range. By using random effects, we are modeling the unexplained variations through variance. This means that our question is basically changed a little bit. So we still want to know whether there is an association between Dragon's body length and the test score, but we also want to know if this association still exists after controlling for the variation in the mountain ranges. So in order to fit the random effect, we are going to use the syntax that we've got in here. So in here, we are saying that we are interested in the relationship between test score and body length being the fixed effect, and the random effect is going to be the mountain range. Okay, let's run this and look at the summary. So once we account for the mountain range, it's obvious that the Dragon body length doesn't actually explain the differences in the test score. So take a look at the summary output. One thing you would notice is that the model estimate is smaller than its associated error. That means that the effect or slope cannot be distinguished from zero. So one thing to keep in mind is that the random effect of the mountain range is basically meant to capture the influence of mountain ranges on Dragon test score. Whether we observe those influences explicitly or not, whether those influences are big or small, and so on. It could be many small influences that, when combined, would basically affect the test score, and that's what we are hoping to control for. We can see from the variance for mountain range, which is in here 339.7. Mountain ranges are clearly important. They explain a lot of variation in here. The reason why I say that is that we can take the variance for the mountain range and divide it by the total variance, and we are going to get to something like this. 0.6. So 60% of variation, or 60% of variance, is actually coming from mountain range. So the differences between mountain ranges explain something around 60% of the variance that's left over after the variance explained by our fixed effects. And it's always a good practice to have a look at the plots to check our assumptions. So let's plot this model that we created. We are going to have something like this. And let's also take a look at the QQ plot. And put the line. Okay. Everything seems quite good, with some variations, small variations at the extremes, but that's really it. Okay, the next thing that we want to discuss in here is types of random effects. Okay. Okay, we are going to use a data from a workshop. Okay, I'm not going to go through too much details about these different types of random effects because this is quite an advanced topic, which more than anything, it kind of requires some certain level of expertise in order to do it. But at the same time, I think we can spend a couple of minutes so I can show you two examples. One of them is a wrong way of modeling and the other one is the right way of doing the same thing. So give you some hint about the possibilities when you're doing something like this. So in general, we kind of have two types of random effects. They can be considered as cross or nested. So let's start with cross. So there are some hierarchical linear models, or also called multi-level models. While all of these HLMs or hierarchical linear models are mixed models, not all of the mixed models are considered as hierarchical. That's because you can have crossed or partially crossed random effects that do not represent levels in a hierarchy. Think, for instance, about our study where we are monitoring dragons, which is considered as a subject, across different mountain ranges, which is the context. And then imagine that we collect multiple observations per dragon by giving it the test multiple times. And by doing so, we are gonna be risking pseudo-replication. We are gonna talk about this later on. But since the dragons basically can fly, then you can imagine that, for example, in this hypothetical data set that we've got in here, we might observe the same dragon across different mountain ranges, but also that we might not see all the dragons visiting all of the mountain ranges. So as a result, we can potentially observe every dragon in every mountain range, which is called cross, or at least observe some dragons across some of the mountain ranges, which is called partially crossed. We would then fit the identity of the dragon and mountain range as partially cross random effects. Now, an effect is going to be considered as fully crossed or just crossed when all the subjects have experienced all the levels of that effect. Now let's talk about the nested random effects. You can imagine them as these Russian nested dolls. I also mentioned the hierarchical models, which is basically the definition for the nested effects. So there is often an element of a scale or sampling a certification in there. So let's assume you have a fertilization experiment on seedlings growing in a seasonal forest and took repeated measures over time, let's say 3 times per year in each season. Now, considering this fertilization experiment, let's say you have 50 seedlings in each bed with 10 control and 10 experimental beds. That's going to be 1,000 seedlings altogether. And let's say you went out collecting once in each season in each of the 3 years. So on each plant, you measure the length of 5 leaves, for example. So that's going to give you something like 5 leaves by 50 plants, by 20 beds, by 4 seasons, by 3 years. It's going to be 60,000 measurements. But if you were to run analysis using a simple linear regression, something like, for example, leaf length tilde treatment, for example, you would be committing, you would be basically doing a very wrong thing. Which is the reason for it is because you are having pseudo replication or massively increasing your sampling size by using non-independent data. With a sample size of 60,000, you would almost certainly get a significant effect of treatment which may have no ecological meaning at all. And it also violates the assumption of independence of observations that is a central point to linear regression. This is where our nesting dolls idea basically comes in. So leaves within a plant and plants within a bed may be more similar to each other for genetic and environmental reasons. You could, as a result, add some random effect structures that account for the nesting. So, for example, you could say something like this. You could say something like leaf length tilde treatment plus bed. Sorry, this should be like this. Bed, plant, leaf. Something like this. So you could have a formula like this. This way, the model will basically account for non-independence in the data. And then the same leaves have been sampled repeatedly. Multiple leaves were measured on an individual. And plants are basically going to be grouped into beds which may receive different amounts of sun and so on. Now, what about the cross effects? If all the leaves have been measured in all seasons, then your model would become something like this. Instead of let me close these. So instead of these, you could say something like leaf length tilde treatment plus 1 on bed plant leaf plus 1 over season. So to make things easier for yourself, you should basically try to always avoid implicit nesting. So let's get back to our study and see how we are going to do this. Here we are. We collected the data on dragons, not only across multiple mountain ranges, but also across several cities or several sites with those mountain ranges. So if you don't remember this, let's take another look at it. Here it is. Where is the head of this? There we go. Here is. Here is the head of the dragon. So we have test score, body length, mountain ranges, site, and body length. And we could also look at the STR of this. So test score and body length are a number, mountain range is a factor, X is logical, site is factor, body length is a number. So the same way that we deal with mountain range, we have to assume that data collected within our sites might be correlated, and so we should include sites as an additional random effect in our model. Our site variable is a 3-level factor in here. And in there we've got things like A, B, and C. So the nesting of the site within the mountain ranges is going to be implicit. So our sites are meaningless without being assigned to specific mountain ranges. And there would be nothing like site B of the Bavarian mountain range with site B of the central mountain range. So to avoid more confusion, we should create a new variable that is explicitly nested. So here we go. Within our dragons, we create something called sample, which is a factor version of mountain by site. Now, it's obvious that we have 24 samples. We had 8 mountains, and this is multiplied by 3 factors. 3 sites. So 8 by 3 becomes 24. So now we've got Bavarian A, Bavarian B, and so on. And we should use this instead of using the site in our model. Each site belongs to a specific mountain range now. Now, let's get to our model again. We are using LMER in here again. We said test score by body length plus 1 over mountain range and plus 1 vertical sample, data being the dragons. Let's look at the summary. So if you look at this perfectly, you would notice that if I get this summary, there are 24 samples, 8 mountain range, there are going to be 3 sites. And this grouping is really wrong. This is not the correct grouping that we wanted. Instead, we can go ahead and fit a new model, one that takes into account both the differences between the mountain ranges as well as the differences between the sites within those mountain ranges by using our sample variable. Our question is going to be, or hypothesis is going to get slightly changed again. The question would come to something like this: Is there an association between body length and intelligence in dragons after controlling for variation in mountain range and sites within mountain range? So in order to do that, we are going to use this line of code. So we are creating a new model. Again, we are using LMER in here, which is looking for the association between test score and body length, with controlling for random effects on mountain range and on sample. So let's run this and take a look at the summary again. Here we are trying to account for all the mountain ranges level and all the site level influences, and we are hoping that our random effects have soaked up all these influences so we can control for them in the model. Okay, something to clarify, because I didn't want to record the previous video again. I made one mistake when I was explaining this, and the mistake was basically coming from here. So let's look at this is the wrong version. That I mistakenly basically ran the right one twice. So if we were to basically do this in this way, so if we were, instead of looking on the random effect of the samples, we were to look at the random effect of sites, we would have seen something strange. And that would be this. So here it goes. If you look at the number of observations, you've got 418 here, and in your groups, you've got 8 mountains and 3 sites, but you're not supposed to have 3 sites. So that was the wrong model that we were using. So in order to fix that, instead of taking into account the random impact of site, we would take into account the random impact of sample. And the sample was basically holding the appearance, the association between site and mountain range. So when we run this, take a look at this line. When we run this, the summary is no longer going to include the site. It's holding for the impact of samples instead. You can see in here the intercept is on site. In here the intercept is on sample. So here we are. Okay, let's visualize this again. In order to make things easier for myself, I am gonna make these chunks of codes disappear so I don't get myself confused for a second time. Okay. Now we want to visualize the outcome and see what's going on. So we are using ggplot in here with dragons. X is going to be the body length, y is going to be the test score. The color is going to be based on side. We have a facet wrap on the mountain range with 2 rows, and we are having a scatter plot, so we are calling GM point, and we've got the classic temp, and we are also adding a line, which is the data for it is going to be the sequence of dragons, and with prediction of mixed LMER 2. And it has another thing that we define there. And remember, even though we define this object name, but because we put these parentheses around it, it actually draw it as well. Okay, here we go. Let's make it a little bigger so we can have a better time seeing this. You might have noticed that that all the lines on the figure are actually parallel, almost parallel. That's because so far we have only fitted random intercept models. So a random intercept model allows the intercept to vary for each level of the random effect, but keeps the slope constant among them. So in our case, using this model means that we expect dragons in all mountain ranges to exhibit the same relationship between body length and intelligence, which is going to cause a fixed slope. Even though we know that some populations may be smarter or dumber to begin with. That would be the definition for a random intercept. Now, the reality of the case is that in most of our studies, we have to assume that not all populations would basically show the exact same relationship. We often want to fit a random slope and a random intercept model. So maybe, for example, the dragons in a very cold versus a very warm mountain range have basically evolved differently, body-wise, to basically deal with the heat conservation, and may therefore be smart even if they are smaller than average. So we only need to make one change to a model to allow for random slopes as well as intercept, and that's adding the fixed variable into the random effect brackets. So let's look at it one more time. Here we are. We've got our linear mixed model, which looking for the association between test score and body length, with random effects on 1 plus body length on mountain range / side, with data being from dragon. What we are saying here is let's model the intelligence of dragons as a function of body length, knowing that populations have different intelligence based on baselines, and the relationship may vary among the population. and here is the summary of this.
We are gonna be done with comments.
Now let's plot this. We are using the same plot. We've got our Joe lines, which is based on the prediction of the random slope. In here, it was the prediction from mix LMER2, but in here we are using the prediction on mixed random slope, which is the new object that we created in here. Okay. Now what we've done is that we fitted a random intercept and random slopes. We fitted random intercept and random slope, random intercept mixed models, and now you know how to account for hierarchical and cross random effects. Or let's say you basically had exposure to them. I hope this this introduction would basically help you to better understand the basics of linear mix effects and how. I'm gonna stop it here. So I will be putting the link to this videos inside through an announcement in Canvas, if you wanted to take a look at it. And I'm also going to upload the code for it with the data, if you want to play around with it. But there, you really need to look at this a couple of times in order to figure out how I came up with no idea about what is my random effect, to the point of, through visualizing the results, through realizing that I made a mistake in my choice of random effect, and come up with a better formula that would finally capture the actual analysis that I needed to do. Okay, that's the most difficult thing in linear mixed models, to figure out what is going to be the random, what is not going to be random, and what is wrong with your analysis. The moment that you figure that one out, you're good to go. All right, is there any questions? No? Okay, sorry for keeping you here over time, and we will meet next week. Bye, everyone.